in the last class there was a question by him, that was when we were dealing with the equal eigenvalues, then we had said that the solution will be x of t will be C 1 plus C 2 t e to the power, right, that is what we said. But when we dealt with in the earlier classes, then we said that it is actually a combination of C 1 e to the power lambda t plus it would be V 1 V 2 plus C 2 e to the power lambda t, and then you had A 1 plus A 2 t and B 1 plus B 2 t. Now, the reason that I abbreviated this was, suppose you are talking about the first line which is x t and the second line is y t. So, your x t is C 1 e to the power lambda t V 1 plus C 2 e to the power lambda t A 1 plus C 2 e to the power lambda t A 2 t. Now, we can club them as it is e to the power lambda t times So, you see there is a one term with e to the power lambda t, which is with a coefficient that is a constant. There is another term with t e to the power lambda t with another coefficient constant, that is what we have written here. Okay. So, it is just an abbreviation of that. We have clubbed all this together as the new C 1 and all this together as the new C 2, that is all. So, in the last class we had given a problem and asked you to approach it. The problem was that the x vector is 3D, and now that 3D equations are 0 1 0 0 0 1 minus 2 1 2 with x. So, in this case how would you proceed? First you will go the same way, that means we will try to identify the eigenvalues and eigenvectors. We will write the independent equations along the eigenvectors and then proceed. So, what are the eigenvalues of this? In this case the eigenvalues you are already calculated, right. So, eigenvalues are 2 1 minus 1. The next question is to obtain the eigenvectors for each of these eigenvalues. So, what is the eigenvector for 2, what is the eigenvector for 1 and what is the eigenvector for minus 1? Okay. For lambda is equal to 2, 1 to 4. V 1 is 1 2 4, is that right? Have you fellows done it? Okay. For lambda is equal to 1, V 2 is 1 1 1, and for lambda is equal to minus 1, V 3 is
1 minus 1.
Is it visible? Yes, 1 minus 1 and 1, right. So, now we can compose the general equation as x of t will be C 1 e to the power twice t 1 2 4 plus C 2 e to the power t 1 t actually 1 1 1 plus C 3 e to the power minus t 1 minus 1 1, fine, which means the first one x, second one y, third one z, x of t will be C 1 e to the power twice t plus C 2 e to the power t plus C 3 e to the power minus t. Y t will be C 1 2 e to the power twice t plus C 2 e to the power t minus C 3 e to the power t, so on and so forth, and these C 1, C 2, C 3 will have to be obtained from the initial conditions. Is that clear? Now, as we have always done in this class, we will try to develop a geometrical understanding of what happens, what is happening here. You notice that there are two eigenvalues which are positive and one eigenvalue that is negative, which means that there is this eigenvector along which can you show my face? Yes, there is this eigenvector along which it is contractive, that means it comes to the equilibrium point, and there are two other eigenvectors along which it is expansive, that means it goes out. What does it mean? You can imagine then a plane passing through those two eigenvectors which have positive eigenvalues. Okay. Imagine these are two eigenvectors, along which it expands. Now, imagine a plane passing through these two eigenvectors, then the system will be unstable along that eigenplane, right, and it will be stable in the other eigenplane, right. So, these are subspaces of the 3D space. So, we can in general conclude that it will be stable along this subspace and it will be unstable along the 2D subspace spanning these two eigenvectors. Is that clear? So, depending on the eigenvalues and eigenvectors, you will have conditions where even though this space is rather large and on the face of it is somewhat difficult to visualize, you will be still able to concentrate on subspaces that are either stable or unstable given by the eigenvalues. Okay. If an initial condition is along that particular subspace, which is this, then there is no component along these two, and therefore, it will converge directly onto the equilibrium point, fine. If there is an initial condition along exactly this, then there is no component along these two and it will expand as e to the power t. But if there is an initial condition in the plane that is spanned by these two eigen vectors, then there is no component along this, therefore, it will not contract at all and it will expand along that as if it is a 2D system, right, exactly the way it would behave in a 2D system. If you have an initial condition in that plane, it will behave in exactly the same manner, and it will go out, but going out will be dependent on these two exponents. How fast it will always converge onto one of the eigenvectors and then go out to infinity, that we have already learnt, and that is what will happen in this case. So, you see you have the situation if you have three real eigenvalues depicted like this. Supposing you have a different situation where the lambda 1 is say minus 1, lambda 2 is say minus 2, and the lambda 3 is say plus 1. What will be the behavior like? There will be associated with them eigen directions, eigen vectors, but in this case you can see there will be an eigen plane that will be stable. associated with this there will be an eigenvector, associated with this there will be an eigenvector. The plane that passes through these two eigenvectors will be a stable plane, even though this system is globally unstable. Okay. Now, globally unstable means there is an expanding direction. Any deviation along that will be expanding, will be going out. So, why is that important? It is important because if you have to control it, if you want to keep it within that, you do not really need to pay attention to these two. You have to pay attention to this fellow, and you have to do something, some control to push it back along this direction, and it is not going to go out along these directions. And that is why in general it is necessary to understand what are the expanding directions and what are the contracting directions. In this case there will be a subspace that will be contractive, a contractive subspace. Okay.
So how do we find the plane which will contain the two eigenvectors?
Well, start at the origin they meet, and there are two lines, and these two lines will define exactly one plane, right. In a 3D space, imagine they are not just any lines, they are meeting at the origin. At the origin there is one line here, another line here, it defines exactly one plane, right. In a linear system it will be a plane, in a nonlinear system that will be some kind of a general surface, but nevertheless you can imagine, you can identify, right. See, always what I am trying to drive at is that you should be able to sort of close your eyes and visualize that the behavior will be like this, of a system like that. Okay. But then if the system is has real eigenvalues, you can have the four possibilities, either one all the eigenvalues negative, in which case it will be contracting, globally contractive, that means all initial conditions will converge onto the equilibrium point, and while it does so, it should always come closer to first an eigenplane and then a particular eigenvector, and along that it will converge to the fixed point, the equilibrium point. If there is one eigenvalue which is negative, two eigenvalues positive, then we have already seen. Two eigenvalues negative, one positive, we have already seen. If all the eigenvalues are positive, it will again be globally expansive, it will be unstable in all directions, but then it will always converge onto one of the eigen directions and then go to infinity, not just any which way, right. What are the other possibilities? All negative, yes, all negative is the case where you have all converging, in which case that point will be almost attracting all initial conditions from anywhere in the space. Such a point is an attractor. Such a point is an attracting fixed point, attracting equilibrium point, which attracts all initial condition towards itself, as if it is a gravitating body. It behaves like a gravitating body. If you have this kind of situation, in general it is a saddle, right. Our imagination of the saddle was a 2D concept, because we had imagined the saddle something like this, where if you have a marble here, then it will be stable in this direction, any perturbation in this direction will again bring it back to that, but any perturbation in this direction will make it fall. So, it still has the same property. In this case, that was one of the eigen directions and this was another eigen direction. In this case, you have the eigen directions, 3 of them. Not only 3 of them, I am also introducing the concept that 2 will introduce a plane which is a stable eigenplane or a unstable eigenplane. Clear? Digested? Okay. If you have digested this, then let us go on to the situation where there could be complex conjugate eigenvalues. First, let us deal with the situation where there are purely imaginary eigenvalues. Consider a system with x dot is equal to 1, 2, 0 minus 1 minus 1 0 and 1 0 minus 1 x. What will be the eigen values? Quickly do this. It will be 1 minus lambda 1 minus lambda, so it will be times 2 0 minus 1 minus lambda 0 and all that. Just write it correctly. So, it will be a minus lambda I, it's equal to 0. That is the concept. Lambda I will be here, here and here. So, you have to obtain the determinant of this 3 by 3 matrix. That is what we started doing. This term will become 1 minus lambda, this term will become minus 1 minus lambda. So, whose determinant? It will be 1 minus lambda 2 0 minus 1 minus 1 minus lambda 0 1 0 minus 1 minus lambda. So, what has it yielded? So, if you solve this, you are getting lambda is equal to minus 1 plus minus j, fine. Okay, so there will be an eigenvector associated with minus 1, there will be an eigenvector associated with plus j, and as we have done already, we will not bother about the minus j component, because that gives no further information, no new information. So, just go ahead exactly in the same way. First, what is the eigenvalue associated, eigenvector associated with minus 1? A minus lambda I x equal to 0. From here, what are we getting? Well, let me do it, since you seem to be a bit confused. Okay, let me do it. A minus lambda I will be 1 minus lambda 2 0 minus 1 minus 1 minus lambda 0 1 0 minus 1 minus lambda x y z, fine. The first one says 1 minus lambda x, okay, lambda is in this case minus 1 2. So, twice x plus twice y is equal to 0. Second one is this is minus 1 0 0. So, x equal to 0. Yeah. So, what will be zero zero? Yes. So, just assume anything as z, it will give it, say 1. So, x is 0, this is says y is 0, and z could be anything, therefore, it is actually in that direction. So, z could be anything, say it is 1. So, in this case it gives 0 0 1, right. Similarly, you do this for say plus j. If you take it as plus j, let me do it because it might be a bit confusing. 1 minus j 2 0 minus 1 minus 1 minus j 0 1 0 minus 1 minus j x y z is equal to 0. Fine. So, you have 1 minus j x plus twice y is equal to 0, first equation. Second equation is minus x minus plus minus 1 minus j y is equal to 0, and third equation is x plus minus 1 minus j z is equal to 0. Okay. What will satisfy these? 0 0 no, no, you cannot say 0 0 0 obviously that is not a good result. So, this is
if you take z equal to 1,
okay, z equal to 1. Okay, his suggestion is, let us say z equal to 1, z equal to 1 means it will be
minus 1,
huh?
z equal to 1 means y equal to minus 1,
Okay.
x equal to 1 plus j.
Y equal to minus 1 and x equal to
1 plus j.
fine. So, your eigen vector is 1 plus j, y is equal to minus 1 and z is equal to 1. Great. Is the concept clear how to obtain it? Good. So, you have this and you know that it has two parts, 1 minus 1 1 and j 0 0. There are two parts, one real part, another imaginary part. Fine. So, let us now proceed with this. If you proceed with this, you have the solution as for this one it was known, for this one it is that. Fine. So, there are three solutions, x 1 for, I will write capital, x 1 is equal to, for this eigenvalue and this eigenvector, it is e to the power minus t 0 0 1. Fine. Second one, x 2, now that we have already done. If you have, where is it? If you have this as the eigen vector and plus j as the eigenvalue, it will be, it will start, you start by writing e to the power j t, then this 1 plus j minus 1 1, right, and then we will follow exactly the same procedure that we did earlier. This will yield cos plus cosine plus j sin omega t, and then we will separate the real part and the imaginary part. Fine. After having done so, we will say the real part gives one possible solution, the imaginary part gives another possible solution. Just obtain the two solutions then. Clear? Cos t plus j sin t, 1 plus j minus 1 1. This yields cos t, I'll write separately, x2 is equal to, there are two parts, cos t times 1 plus j cos t plus j cos t plus j sin t minus sin t, fine, the first line. So, I have just separated them out. Second line is cos t minus 1. So, minus cos t plus minus j. So, j minus sin t, no, then I have to talk about the third one is cos t plus j sin t, fine. Now, we separate them out, we will say that x2 t is this part which is cos t minus sin t minus cos t cos t, and x3t is equal to this part cos t plus sin t minus sin t and sin t. Done. So, we have x1 and we have x2 and x3. x1 was this, and then we have x2 and x3. Now, just write down the final solution. So, your final solution x t is equal to c1 e to the power minus t 0 0 1 plus c2 cos t minus sin t minus cos t cos t plus c3 cos t plus sin t minus sin t. So, that is the solution. Happy? This is how it is to be obtained. See, we have produced a method and any problem can be approached by that, any given problem. So, your x t is c1 times this, which is non-existent and all that. You notice that it gives a sinusoidal solution, but it decays along z direction. Can you see that from this? Now, let us figure out what will be the behavior in the 3D state space. Yes, now it is interesting. Why? Because there is an eigenvector which is associated with a negative eigenvalue. A negative eigenvalue means contractive. So, there is an eigen direction z direction along which it is contractive, fine. So, any deviation along that will be exponentially decaying, fine. But if there is a deviation along that, what will happen to that? It will not decay. No, wait, slowly. I am saying that here is a direction along which it is contractive. So, I have given some deviation along that direction which I know will decay, but I have also given a deviation along the orthogonal direction to it. That means, it is away from that eigen direction. What will happen to that component? Yeah, that component will not decay, but that component will cause a with the oscillation motion like this. Okay. So, this component will decay. So, it will be going like this. obviously it will converge onto something, because exponential decay, that means that part will converge onto something, onto what? Yeah, where is the remaining eigenvector? That has to be real. That has to be real. So, see, a plane in the 3D space has to be a real plane. You should be able to visualize where is the plane, and if you have complex plane, you cannot visualize that. Now, that is essentially the plane formed by the two real part and the imaginary part of the eigenvector that we started with. See what we did, we took this, we used that to write down the equation and then separate the real part and the imaginary part, saying that the real part and the imaginary part separately contain the information. Fine. So, these are the two things, two components of the vector, real and the imaginary. So, the eigenvector was was 1 plus j minus 1 1, which is 1 minus 1 1 plus j 1 0 0. You are right. This is a real vector and this is another real vector, and we have composed the final solution in terms of these two real vectors really. So, there will be a plane passing through these two real vectors, the system will ultimately converge onto that plane. The system will ultimately converge onto that plane. So, that is the eigenplane. In case of purely imaginary eigenvalues, the eigenplane associated, there is always an eigenplane associated with purely imaginary eigenvalues, and that eigenplane, real plane, a plane that can be drawn, visualized, a real plane has to be identified from the real part and the imaginary part of the corresponding eigenvector. Is that clear? So, in this case the behavior will be something like this. Say it was x, y, z. In the z direction, it happened to be contractive like this. That just happens to be one of the eigen directions. So, if you start from here, it will just converge here, but if you start from here, it will go like this, but it is natural intuition of many students that it will converge onto the xy plane. It will not. It will not converge onto the xy plane, rather it will converge onto the plane that is spanned by these two vectors. This is the x coordinate, and this is not. It will converge actually onto an inclined plane, and then in that inclined plane, what is the behavior? A circle. So, imagine that if this is the inclined plane, then finally it goes like this, and is that clear? Clear, digested? Now, if I slightly change the values, this was a purely imaginary case. If I slightly change the values, say I make say 1.2, 1.1, something like that, what will happen? It will no longer remain purely imaginary, it will become complex conjugate. So, instead of taking each value, let us try to visualize what will happen if you have complex conjugate eigen values. Two can be complex conjugate, one will always be real. So, what are the possibilities? Possibility 1, that real eigenvalue is positive. Possibility 2, the real eigenvalue is negative. regarding the complex conjugate, there are two possibilities. The real part of the complex conjugate is positive and the real part is negative. There are 4 possibilities. So, let us write down the 4 possibilities and let us figure out what will be the behavior without solving equations. Now, we can close our eyes and figure out the behavior from the general geometrical description. 1, real eigenvalue negative and real part of complex eigenvalues in that case what will be the behavior? In both the directions it will be decaying, but remember that there is an eigen direction, eigen plane associated with the complex conjugate eigenvalues, and along the other eigen direction it will exponentially decay and converge onto that plane, and then in that plane, because of the real part of the complex conjugate eigenvalues, it will spiral inwards. Yes, 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 it will form a shape like a screw. It will be, well, screw when we think, screw when we think, it is not exactly like this. Suppose you have this plane as the eigen plane evaluated the way I have just shown, eigen plane associated with the complex conjugate eigenvalues, and suppose this is the real eigen direction. Then the behavior will be, say starting from here, it will be it will yes, like a screw, all right, but it will not be just like that. Remember, ultimately it will converge and then on this plane it will clear, it will converge onto this plane and then on that plane it will finally home onto the equilibrium point. So, see, I did not solve any equation, just from the concept we can infer that this will be true. The equations will give the details, but it is the concept, geometrical concept, that ultimately matters for us. That is what we are trying to develop. So, that will be situation for, okay, whether or not this decay is faster or that decay is faster depends on that, the real part and this real part. If this real part is more larger, that means larger negative, then what will happen? Yes, it will first converge onto this line and then it will, okay. So, whether this picture will true or this picture will true, it will be dictated by the magnitude of the real parts of the eigenvalues. Obviously, there is an oscillation here, that oscillatory component will be given by the imaginary part, So, the oscillatory component sin omega t omega will be given by the imaginary part. In this case, we had all the sin t's because the imaginary part was 1, that is why, otherwise there will be values there. Done? Okay, let us come to the next situation. Real eigenvalue negative and real part of complex eigenvalue positive. Then what happens? Again there will be a plane associated with that complex eigenvalue, fine, and there will be an eigen direction associated with the negative eigenvalue. This is negative, so it is contracting, and this is 0 0 0. This is the origin, or in this case the equilibrium point. This plane is then a unstable eigenplane. Start from here, it will exactly go there. Start from a close neighborhood of it, it will decay in this direction, it will expand in this direction, and due to the influence of this eigen direction, from here itself it will see the component expanding. So, it will be fine. So, this on this it will be e to the power lambda t, which is positive, times a sinusoid and in this direction it will be just a decay. Happy? Again, in this case, which one will be dominating depends on the magnitudes of the eigenvalues. It may be so that it will very fast converge onto this plane and then will go around, or it will be slow and finally assume a large value even before reaching this plane. That is possible. That depends on the magnitude of the eigenvalues. Third case, real eigenvalue positive and real part of complex eigenvalues negative. In that case, what will happen? There will be a plane associated with this, and there will be a direction associated with that. Then what? It will go away and in this direction. So, this has a outgoing vector direction, while this is negative. So, start from very close to here, it will go like this. Okay. Now, these orientations will be given by the exact differential equations, where this will be, where that will be, you should be able to see that. Or if you, now that you have written down the program for solving any differential equation, take any given 3D system, set the parameters such that you have this kind of combination, and then see the result in 3D. If you are solving by MATLAB, it has a possibility of plotting in 3D, or you can use any other program. For example, I use GNU Plot, it has a 3D plotting program, but the moment you do that, you will be able to see these planes, planes not drawn as planes, but you see that it is converging onto that plane and then it is going out or something like that. Clear? And now the final one, fourth, real eigenvalue positive and real part of complex eigenvalues positive. In that case, again there will be some kind of a plane, and there will be, where is that? This is unstable, that is unstable. In both directions it will go out, fine. But then that is why when we start to depict it, we will have to take a point very close to the equilibrium point. But then whether it will expand faster along this direction or it will expand faster in that direction will depend on the eigenvalues, magnitudes of the real part of the eigenvalues. So, in one possibility what will happen is that it will expand faster here, or also go that way. In other case it will be expanding faster that way and slower this way. So, let us depict that. It will be okay. The behavior will be like that.
So if it is starting from the unstable eigenplane, and if there is no disturbance in that in the real eigenvalues direction, then there will be spiral in the plane itself.
Yes. Yeah. If it is starting from that eigenplane, unstable eigenplane, and there is no disturbance in this direction, no fluctuation or perturbation in this direction, then it will simply go like this. Okay. Fine. So, this is the general picture that can happen in a 3D system. So, at the face of it, the 3D system looks somewhat difficult, but that is how. Remember, here we are talking about only the local linear neighborhood of the equilibrium point. We are not talking about elsewhere, because in general we have seen when we were dealing with obtaining the differential equation, we saw that most of the cases it will be non-linear. So, we argued that okay, we will first take a look at the local linear neighborhood. So, all these pertain to local linear neighborhood. What if the system itself is 4D, 5D, 6 dimensional? Then no, don't get worked up about it, because all that will happen. See, all these concepts are slowly built up, because that should not be difficult for you to visualize. For example, a 4D system, what can happen? After all, there will be eigen spaces, subspaces. There could be a 3D subspace that is contractive and one subspace that is expansive. There could be a 2D subspace that is contractive and the 2D subspace that is expansive, right? These are the possibilities, and in those 2D subspaces there could be a complex conjugate eigenvalues or real eigenvalues. So, these are the possibilities, but now once we are equipped with this, it is not difficult to visualize that. Now we know that these are all that can happen. It can either converge onto that or expand onto that, and if it does expand, then it will be along these directions. That is all that will happen, nothing very big about it. So, the general idea is that for any given system, whatever the dimension, you can always identify some subspaces that will be contractive, some subspaces that will be expansive, some subspaces where there is no oscillation, some subspaces there will be an oscillation, right. So, any system you will be able to identify such subspaces, and this is very important in terms of the general geometrical concept, to be able to identify those subspaces. And in general, these are not difficult. All that will happen, the thing that will really give you trouble is to write down a 4-dimensional or 5-dimensional matrix and obtain the eigenvalues. Beyond 3D, I will not ask you to do that. Just give the task to MATLAB or some other program. You can, it will give you. It will give you the eigenvectors also. So, no problem, you can always play with that. So, from here onwards, you will not do it by hand, you will do it by some kind of computer program, but always the objective will be to obtain the eigenvalues, eigenvectors, and visualize the behavior of the system in terms of that. Fine. Now, some or many of you may have done some course in control theory. Have you done? Some people have done, some people have not done, does not really matter, because we are going completely parallel to it. Those who have done, for them let me tell you something, that the almost the whole of control theory pertains to the local linear neighborhood of equilibrium points. That is why in a control theory we generally try to operate something at the equilibrium point, and whenever there is a deviation from the equilibrium point, we try to control it back. That is why we mostly assume the deviations to be small, so that the local linear approximation is valid, and that is why almost the 99% of the control theory concerns linear models. Means these things that we dealt with. But in control theory, we take a certain slightly different route in solving the differential equations. We take the Laplace transform route. While studying the Laplace transform, we have learned that that offers a nice way of solving differential equations. So, that is how we solve differential equations, and that then use that to obtain controllers and stuff like that. But here we have taken a slightly different route. Those who have done a control theory should be able to relate the two. In what way? In control theory, you do like the transfer function, then we talk about the roots of the transfer function, and the moment you look at the similarity, you will find the roots of the transfer function are nothing but the eigenvalues of the matrix that we have obtained. So, whatever we have concluded in terms of the eigenvalues of the matrices, you would conclude exactly the same things in terms of the roots of the transfer functions. So, when you study those things, or those who have not studied control theory yet, someday you will, then just keep that in mind, that what we are studying now were studied in a different perspective, different way, where in this course we are mainly dealing with the time domain behavior. How does the system evolve with time? Here we are concerned mainly with that. While in a control theory course they are mainly concerned with stability and stuff like that, but here we have understood that the stable, when will a system be stable? When either the eigenvalues are real and negative, or complex conjugate and the real part is negative. So, in general, if this is the Argand plane, this side, the negative side represents the stable eigenvalues. But this has also given us the idea that if a system is unstable, do not try to control it in a blind way, rather give more attention to the unstable direction, try to push it back in that direction. It is possible.
So what about the imaginary axis? Can't we call the sustained oscillations?
Yes, if it is exactly on this, it will be sustained oscillation, exactly complex conjugate the imaginary eigenvalues. So, it will be exactly sinusoidal oscillation, undecaying oscillation.
That we can call stable in a different sense.
It is called marginally stable, in a different sense. Yes. See,
Sir, how does the state variable, how does the plot of state variables, that is on y axis there is one state variable and on the x axis there is one state variable, how does this plot help us more than just time domain plots of each of the state variables?
Okay. Supposing you have something like this, this plot is where you are plotting it in the state space, where the x, y, z are the coordinates. While he asks, if you have the individual plots, say x versus t, y versus t, and z versus t, then what additional information does it give? No, actually this and that contain the same information, but this is a visually appealing. If you look at the waveforms here, how will it look? For example, and waveform like this, how will it look here? And here, and here, do you see? Do you see the structure? No. It is just conceptual advantage. But ultimately what happens? What are you interested in? How does this vary with time? How does that vary with time? How does this vary with time? Ultimately you are interested in this, but this does not give the conceptual clarity which is offered by this. Not only that, this will be invaluable when we deal with nonlinear systems, when we expand our views to say, okay, so far we were considering only the linear neighborhood, now we talk about elsewhere, then this simply does not help. Then you have to look at what is happening elsewhere. Around this particular representation is fine. Go away from this, then you no longer can count on your linear description. then you need to look at it this way. That is the only way you can look at it then. That is why I am slowly building up. So far as only the linear system is concerned, this is fine. But see, we are dealing with dynamics in a general sense. We first looked at the small part and then we will expand, and in order to do that we need this. Okay, now I will give you some problems so that you can do in the tutorial. So, in all these cases you have to find out what is the behavior. Written? A third order system has eigenvalues one, 2 is this, lambda 3 is So, in this case describe the behavior starting from any initial condition close to the origin. Okay? Enough, that is all. Thank you very much.